Okay, so let's state Ionescu-Tulcea theorem. So there exists a probability measure pi on omega f, where omega f is this standard canonical space, such that when you look at pi on finite dimensional measurable rectangles like this, d0, d1 to dn, and after time n, you just take the full spaces, okay, forever. This is the same, this should give the value of the measure pi n at this measurable rectangle d0 to dn. For each d0 in E0, dn in En, and n in Z plus, or let's say n in n. Or, yeah, because pi 1, we start from pi, well, pi 0, that's right, n in Z plus. Okay. Moreover, pi is the low of x. Pi n is the distribution of x0 to xn for each n. So we're not going to prove this theorem because the proof relies on, the proof uses Kara-Theodori's extension theorem. Omitted. So it is technical and long. So we omit this. But this theorem is quite important. Well, all you do is to specify the distribution of x0, the conditional distribution of x1 given x0, the conditional distribution of x2 given x0 and x1, etc., etc. And the theorem says, okay, good, there exists a probability space on which there is a stochastic process whose law is pi and whose finite dimensional distributions are exactly as you specified, okay? So this pi n, right, is what? d0 to dn is just the probability that x0 is in d0 and xn is in dn. I should write pi equals p here, right? This is the p that we take. So in other words, the answer to the question of existence, namely this question in the red box, is positive. There is a similar theorem in continuous time, but it requires some consistency condition, which takes some time to state. That's why I chose not to discuss it with you in this course. But so in a course on stochastic processes, that would be one of the first theorems, probably. But the discrete time case is already rich enough, And I'd like to discuss with you some examples of processes in discrete time. Okay? Some processes in discrete time. So the first example is a sequence of independent random variables. Independent sequence. So we have to specify nu0, k1, k2, etc., right? So let's take nu0 as nu0. Well, okay, given nu0, okay. What is k1? x0 and dx1. So let's assume that this is simply a measure. Measure, meaning that it does not depend on your initial position. Your conditional distribution at time 1 given your position at time 0 is just a measure, is just free of your initial position. Right? This says it is free of x0. Free of x0. K2 is x0, x1, dx2, and this is nu2 dx2. Okay? Again, free of x0 and x1, etc., etc. So in that case, the so Ionescu Tulcea theorem gives a stochastic process, a discrete time stochastic process let me write it xn, okay, which is just a sequence such that the distribution of x0 to xn is nu0 to nu n. Right? This pi n was simply nu0, k1, k2, kn, but those kernels are now just measures, free of their first variables. Okay? So, in fact, the distribution of x0 is nu0, the distribution of x1 is nu1, x2 is nu2, and x0, x1, x2 are independent. When we say let xn be a random variable with distribution nu n for each n, this is a valid statement. Such a sequence exists. So whenever we say, let x0 be a random variable with the exponential distribution, let x1 be another random variable with the Gaussian distribution with mean 0 and variance 1, let x2 be a random variable whose distribution is gamma with some parameters, and there is a long list, infinite list, well, it is fine. Whatever distributions you specify, such a setting exists. Okay? So don't worry about the existence of such a setting, such a sequence of random variables. So this is all fine. And a special case is that if nu0, well, if all spaces are equal and all the distributions are the same, then we have an IID sequence of random variables. IID means independent and identically distributed. So each xn has the same distribution, and x1, x2, x3, they are independent. Oh, okay. Well, I guess we have to explain what we mean by independence of an infinite sequence, infinite collection. We never define this. So we say that an infinite collection of random variables, but this is also true for sigma algebras. If you have an infinite collection of sigma algebras, are independent if every finitely many of them are independent. Okay? And indeed, x0, x1, so these are independent if and only if this x0 to xn are independent for each n. That's what we mean by independence of an infinite collection of random variables, or also sigma algebras. Another example is Markov chains, which is discussed a lot in undergraduate courses on stochastic processes. So it is a good time to discuss why they exist. Okay? So let's pick that the state space is the same, okay? E0, E1, etc., all E. Okay? Again, we are in discrete time. And suppose that, okay, so we have nu 0, the initial distribution. So we have K1, okay, which is a kernel from from space number 0 to space number 1. Now, here's what we're going to assume. The second kernel, so x0, x1, dx2, is only a function of x1. So we're going to write p2, x1, dx2. Dependence on x1 only. Okay? Remember Markov property from undergraduate courses. So the conditional distribution at time n, given all the history, is the same as the conditional distribution of time n, given the previous time step, which is just x1. So let's call it p1. Kn is x0 to xn minus 1 dxn. So this is now just pn xn minus 1 to dxn. Okay? Free of the other variables. That's what I mean by this. This is free of x0. Namely, for all x0, this is just equal to this. Okay? And it continues like that. So now a process with these finite dimensional distributions is going to have what? So x0, x1, etc. with, let's say, x0 to xn with distribution nu 0 p1 to pn, right? This is for all n. So a sequence with those finite dimensional distributions is called a Markov chain. Markov chain with state space E. State space E. This other script E is, again, they're all equal, okay? So if P1, P2 are all equal, then we say that the chain is what? So if P1, P2 are all the same transition probability kernel, one-step transition probabilities, what do you call it? What kind of a Markov chain is that? The conditional distribution at time 1 given time 0, the conditional distribution at time 3 given time 2, the conditional distribution at 25 given 24, they're all the same probability kernel. Time homogeneous, exactly. It's called time homogeneous. Okay. For instance, using those kernels, you can calculate a probability like this: x0 in D0, x1 in D1, x2 in D2. So what we need to do is to condition on the first step, right? So we want to end up at D2, right? So if our distribution, if our position at time 1 is given, then this is the probability that we're going to end up at set D2. But this x1 should be in D1, therefore we need to integrate it with respect to our conditional distribution at time 1 given our position at time 0. So this we need to integrate over D1. And finally, we need to know our initial position. So this is going to be nu 0 dx0 over d0, right? Over d0. And this is simply p2 of x1 d2. I just wrote it as an integral for fun. Initial distribution, it's the conditional distribution of x1 given x0 is x0, and this is conditional distribution of x2 given x1 equals x1. In undergraduate courses, of course, you discuss Markov chains with finite or countable state spaces, mostly finite state spaces. In that case, if you have only finitely many states, then you don't need kernels, but it is just enough to have transition probabilities, which you can calculate from a transition probability matrix. Remember when we introduced matrix, transition kernels for the first time, one of our examples was about the finite case, where the transition probability kernel reduces down to a stochastic matrix, a probability matrix, right? So indeed, with Markov chains with general state spaces, we can use kernels, which just extends those calculations with transition probability matrices. Transition probability matrices. Okay. So I think if you like, we can even write it as follows. So let me write the exact meaning of P2, x2 in dx1, given x1 is equal to little x1, right? So this needs to be integrated over d1, d2, d2. Okay. Now this needs to be integrated with respect to the conditional distribution of x1 given the position at time 0 over d1. And finally, this needs to be integrated with respect to the distribution of x0. And this is simply probability that x2 is in d2 given that x1 is equal to little x1. So we just briefly discussed those processes. And there is one more process I'd like to discuss with you in slightly more detail. And these are Bernoulli processes. Bernoulli processes. So I'd like to give it as an additional section, as a separate section. So these are the processes appearing in infinite coin tossing spaces. Infinite coin tossing. Okay. And so just as a recall for Bernoulli variables, so let's say we have a probability space. So recall that a random variable z from omega to 0, 1 is called a Bernoulli random variable, right? Bernoulli random variable. And so we may write it as z equals the indicator of an event, where A is simply the event that it takes the value 1. Okay? And the probability P, which is the probability of A, or the probability that z equals 1, is called the success probability of z. Well, the idea is that whenever we get heads, we call it a success. So the case that z equals 1 corresponds to the case where we get heads, and the other one, a complement, is the case where we get tails. So tails is considered as a failure, as a convention, okay? And then the probability of getting heads is the probability of success. It's the probability of success. And indeed, if you like to calculate the expected value of z, it is simply p, right? It is simply p. How about the expected value of z squared? What is the relationship between z and z squared? What is the relationship between z and z squared? Yes? Okay, I can wait. What is the relationship between z and z squared? Exactly. What is the relationship between z and z cubed? Again, same, right? So these are all the same, and they are equal to p, because z is z squared, etc. So its variance is pq then, right? So p, expected value of z is p, so square it. This is p times q, where q is just 1 minus p, right? And also the generating function, which is z to power capital Z, okay? So z, the little z is a number between 0 and 1. Therefore, so this is going to be z to power 0 with probability q, and z to power 1 with probability p. So it's going to be just q plus pz, right? Where z is between 1 and 0. Generating function, which determines the distribution of z, capital Z. Okay, so what is a Bernoulli process? A Bernoulli process is nothing but an IID sequence of Bernoulli random variables. So an IID sequence Zn is called of Bernoulli random variables, of Bernoulli random variables, is called a Bernoulli process. oh, should I use X? Let's use X, okay? Bernoulli process. So we're on the timeline. Well, it's just discrete. And we started from 1. So at each time we flip a coin, and we see if we get heads or tails. Let's say this is heads, heads, tails, heads, etc. So it's a success, success, failure, success. In other words, x1 is 1, x2 is 1, x3 is 0, x4 is 1, etc., etc. And you flip this coin independently every time, and the probability of getting heads is just p. Okay? Since we say IID, so they are independent, and they're also identically distributed. And since we're talking about Bernoulli's, the only parameter of the distribution is just the success probability p. So identically distributed means every time you have the same probability of getting heads. So xn is 1 with probability p for all n. So of course, this is not a very interesting process by itself, because these are just independent things, and you can deal with them one by one. So there's nothing interesting about that. But there are more interesting things. For instance, you can define the number of successes in the first n tosses. So number of successes in the first n trials. Okay. So then you get a process which is not IID, which is not IID. Indeed, S1 can take values 0 or 1. S2 can take the values 0, 1, 2. S3 can take the values 0, 1, 2, 3, etc., etc. So Sn takes values in 0, 1 to n. What is the distribution of Sn? You all know. What is the distribution of Sn? Number of successes in the first n tosses. Binomial with parameters n and p. So why is this the case? Well, you can come up with a combinatorial argument to calculate its distribution, but I'm not going to do that. Instead, I'm going to follow a more rigorous path, which I find interesting. So let's calculate the generating function of Sn, okay? Let's calculate the generating function of Sn, since it determines the distribution of it. Generating function, so z to Sn. What is Sn? It is just x1 to xn. So this is z to x1, z to xn. And since they are independent, it is simply the independent and identically distributed. It is simply one of those generating functions raised to power n. What is the generating function of x1? It is q plus pz. So q plus pz to power n. Well, we all know how to write it down more explicitly using the so-called binomial theorem. So it is just sum of bunch of terms, n choose k. Let's raise this to power k and this to power n minus k, right? Or you can write it as n choose k, p to k, q to n minus k times z to k. So as a function of z, this is a polynomial of degree n, right? It's a polynomial of degree n because the highest power of z is just n. Just n. On the other hand, we have z to Sn. Well, if we knew the distribution of Sn, we could have just calculated this as z to power k times the probability that Sn equals k, right? It's a function of Sn, so if we knew the distribution of Sn, this would have been the way to calculate it, because Sn just takes the values in this set 0 to n. So these two things, let me write zk here, okay? Again, a polynomial in z. These two things are the same. These two things are the same. Same polynomials of z. The variable of this polynomial is z, and z is in the set 0 to 1. So if you have two polynomials which are just equal, okay, this means what? Their coefficients must match. If you have two polynomials that are equal, the coefficients must match. So we should have that this is equal to just this. Must match. The coefficients of all degrees must match. So we conclude that Sn is binomially distributed with parameters n and p, and this simply means that the probability that Sn is equal to k is n choose k, p to k, q to n minus k, where k runs through the set 0 to n. Okay. Well, you can calculate its expected value. It is n times p. The variance is npq. But don't calculate them using the expectation formula. That's going to be tedious. Instead, just look at this expression, right? Expected value of Sn is expected value of x1, dot, 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 expected value of xn. And each has expected value p. Therefore, your mean is n times p. Since they're independent, the same is true for variance. Variance of Sn is variance of x1 up to variance of xn. And each has variance pq. Therefore, the variance of Sn is just n times pq. Right? So you don't need to go through tedious calculations with the binomial distribution, because you can just use the fact that you can see it as sum of independent Bernoullis, IID Bernoullis. Okay. So this is not something about the process Sn. This is just the process at a fixed time. So let's look at, for instance, S10 minus S5 and S4. What is S10 minus S5? It is the number of successes that you get between times 5 and 10, right? Between times 5 and 10. So this is simply x6 to x10, right? This is x1 to x10. This is x1 to x5. So what is left is x6 to x10. And this is x1 to x4. What can you say about these two? x1 to x4 versus x6 to x10. What do we know about xi's? They are IID, right? So what can you say about x1 to x4 and x6 to x10? Are they independent? They must be independent, because these are all, those random variables x6 to x10 are all independent from the collection x1 to x4. So these two must be independent. And moreover, this has the binomial distribution with parameter 5 and probability p. This has the binomial distribution with parameters 4 and p, right? So what we have is that, so we can generalize it to the following fact. So Sn, the process Sn, has independent increments, meaning that Sn plus k minus Sn is independent of this so-called filtration at time n, which is S1 to Sn. Okay? It is the sigma algebra generated by the vector S1 to Sn. So all this is saying is that this increment is independent of the past up to n. Indeed, it is independent of Sn, right? If you took S5, this would be from x1 to x5, which is still independent of x6 to x10. Okay, you can also write S5 here. It's fine. Okay. And this process also has stationary increments. And this means the following. Sn minus k minus Sn has the binomial distribution with parameter k and p. So meaning that it is free of n. So it doesn't matter where you start the increment from. But what it matters is the length of this interval, which is k. You look at k trials from Sn to Sn plus k. Okay? It doesn't matter where you started from. Okay? It is just the length of this interval, which is k. So this process has stationary independent increments, and there is a name for this. It is a Levy process. Okay? Levy process means it is a process with stationary independent increments. Okay? Levy process. Levy process. Okay. What else can we look at here? Do you remember any other interesting distribution related to coin tossing? For instance, you start the game, you flip a coin, tails, 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 tails. When do I get the heads? Time of getting heads is a random variable, right? Geometric random variable, exactly. And indeed, you can also look at time of second heads, third heads, etc. So we can also consider times of success. Let's say tk is the time of kth success. Well, how do we define it mathematically? It is the first time, let me write inf, first time, at which we have k successes for the first time. We have k successes. You can put equality, doesn't matter. Same thing. So on a picture, let's say we have failure, 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 success, failure, 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 success, success, failure, success. This means, so these are 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. So this means T1 of omega is 4, T2 of omega is 10, T3 of omega is 11, and T4 of omega is 13 on this realization. So this is a picture for one possible omega, whatever this omega space, the space of omegas is. Let's look at the probability that Tk equals n. Let's look at the let's try to figure out the distribution of Tk. So Tk equals n means what? So k minus 1 successes among the first n minus 1 trials and success at trial number n, right? So you want to finish it by a success so that you can call it the time of the kth success. So kth success is at time n, that's for sure. But up to that time, we should have k minus 1 successes. Right? These two events are precisely the same. Therefore, I can look at their probabilities. And since these two are independent, so this is simply n minus choose k minus 1, n minus 1 choose k minus 1, p to power k minus 1, q to power n minus 1 minus k minus 1 times a p. Right? So this is n minus 1 choose k minus 1, p to k, q to n minus k. So this is for n between k, k plus 1, etc. It starts from k because it's the time of kth success, so it can be at least k. It should be at least k, or k plus 1, or k plus 2. If everything goes well, I have success, success, success. So at time k is the minimum time I can get the kth success, right? So the values of tk, possible values of tk are these, k, k plus 1, etc., etc. So this is called the negative binomial distribution. Binomial distribution, not a very popular name. The special case k equals 1 is the most popular one, right? T1 equals n is just what? When k equals 1, this is just something choose 0, which is 1, p to power 1, and q to power n minus 1, right? And this is for n between 1, 2, 3, just n, right? So T1 is called a geometric random variable with success probability p. Success probability p. So I need maybe 15 more minutes to complete this discussion for this next time. Then comes convergence. Convergence of random variables, random sequences, let's say. Okay, so that's going to be the last chapter of the semester. But for today, thank you very much, and I'll see you on Friday.